Hola, chaps. Let's learn.
Hola, chaps. Mr. Turek here. In this episode, I'm going to start off by reading an article written by Isaac Asimov. His article title was The Fateful Lightning, and then I'll switch over and go on with my demonstration. Man has been at the mercy of nature throughout his entire existence. If only the proper ritual, the right formula, the right mystic sign, the right lucky object, the right way of threatening or pleading could be discovered, why, then game would be plentiful, rain would be adequate, bad luck would not befall you, and life would be beautiful. The tribal elder, the shaman, the medicine man, the wizard, the magician, the seer, the priest, these are the people the common man turned to for protection from the universe. The point is that well into the 18th century, the universe was either controlled by supernatural forces, whether through spells or prayer, or it could not be controlled at all. Science in the mid 18th century still meant nothing to the general population. Science was viewed as a thoroughly abstract pursuit by gentlemen of high IQ, a pursuit that did not, and many felt should not, involve practical matters. Technological advances, such as catapults, the mariner's compass, the horseshoe, gunpowder, the printing press, were the products of ingenious thinking that had nothing to do with the abstract thinking of natural philosophers. The general population did not consider science as an alternate to superstition. They never dreamed that science could have any application at all to ordinary life. Of all the fatal manifestations of nature, the most personal one, the one which is most clearly an overwhelming attack of a divine being against an individual person, is the lightning bolt. War, disease, and famine affect not only you, but your friends and neighbors, your region, your nation. The person who is struck by lightning, however, is personally singled out. His neighbors are spared and are not even singed. Divine displeasure blazes forth publicly, lending an added dimension of shame and horror to the thought of being its victim. To the Greeks, it was Zeus who hurled the lightning, and to the Norse, the lightning was Thor's hammer. For the Catholic, it was God. Or as Julia Ward Howe says in her Battle Hymn of the Republic, he hath loosed the fateful lightning of his terrible swift sword. And yet, if the lightning stroke were obviously the wrathful weapon of a supernatural being, there were some difficult to explain consequences.
There were some difficult to explain consequences. If you were a highly educated student in the 1700s and you saw a violent storm approaching on the horizon, what should you do? Okay, well, it turns out many of my students don't have the right mindset of someone living in the 1700s. Keep in mind that science is not something that has to do with everyday life. Keep in mind that superstition, prayers, and spells are what protect you from the universe. So if you see a violent storm approaching and you're in Europe in the 1700s, the proper thing to do is to pray. Because when you see that storm coming, that means that God is upset with somebody and you don't want it to be you. So, when a storm was approaching, it would be the job of the bell ringer to run into the church and ring the bell to let the village know that God was getting upset with someone and that they better start praying. Well, as it just so happens, church steeples stick up pretty high above the ground and become a target for lightning strikes. In a 33-year period in just Germany in the 1700s, 400 churches were damaged or destroyed by lightning. And those bell ringers who ran into the church, 120 of them were killed by lightning strikes. So, God can be vengeful. An interesting invention came out in 1745 called the Leyden jar, named after the city where one of the two co-inventors lived. And this is a pretty reasonable model of what it's like. You could make this at home. Please don't, because it is somewhat dangerous. A glass jar, metal on the inside, metal on the outside, and a little connector. And when you foolishly play with this too much, you're going to end up getting a little spark, a little electric shock. This caught the fascination of America's first scientist. One day, he was petting his cat. And so I'm going to use this piece of wool and kind of simulate it, right? So he was petting his cat, and he realized that on a hot day, dry day, as he pet the cat's hair would stand up, and you could hear this little sparkly stuff. And so he wondered to himself, what is it that happened when he pets the cat? He couldn't see anything in his hand, maybe cat hair, but he hypothesized that he was scraping something off of the cat's fur and onto his hand, something he couldn't see, and they were trying to get reconnected back together after he scraped it off. So he could name it whatever he wanted. He chose to name the cat hair positive, and whatever he was scraping off of that, he called that negative. And so 100 years later, when the electron was discovered, that's how it got its name. So in a previous episode, I demonstrated how you could take a piece of wool and a PVC or plastic pipe and scrape it up and get an electric charge out of it, a small one. Now, as it turns out, the conditions where I'm doing this demonstration this evening are just terrible for demonstrating the stuff I want to do. So I'm pretty sure nothing is going to happen when I do this. But I can tell you the story that says, if we were in my classroom and it were a dry day, after I charged this thing up with a positive charge on it, if I were to bring it near a neutral object like this soda can, the neutral object would become polarized, and the closer charges would be attractive, the farther charges would be repulsive, and as a result, this can would actually begin to roll towards the charged object. Whoa, was that the wind? I think you can see on that camera that it's not the wind, because this thing is rolling both towards and away, well, to the left and to the right as I bring the charge nearby without thwacking it. Okay, so it does slightly work. For the experiments that America's first scientist, who by the way is Benjamin Franklin, the same guy who did the printing press, the American Revolution, Franklin stove, lots of good stuff, he did a series of experiments in the summer of 1750. And I could spend all evening scraping this thing, that was the wind by the way, back and trying to demonstrate his experiments, or I could use a machine to help me out. This machine is called the Van de Graaff generator. And the idea is when you scrape two materials against each other, you're scraping electrons off of one. There's a rubber belt on a racetrack shape, there's a motor down below, and at the bottom, the scraping against the rubber against a metal comb causes electric charge to become separated. The charge that's stuck on the rubber belt is brought up inside this hollow metal dome. One thing about electricity is it hates being inside a conducting material. So as soon as it gets up here inside this dome, there's another comb up there touching the rubber belt, and that's where the electric charge exits the rubber belt and goes immediately to the outside of the dome. Sadly, it's a very noisy thing, so from now on, you're just going to have to hear my voice whenever this motor is running. So with the help of Mrs. Einstein, I've put some pom-poms on top of this dome so that you can see the effect of the electric charge on it. So basically, when the charge builds up, like charges repel, and they're willing to climb out onto the palm fronds here, trying to get it away from each other, defying gravity to do it. So when it's on and it's running, you can see the fronds trying to stand up. When I shut it off, you can see it very quickly dissipates into the atmosphere. The humidity right now is 60 or 77%, making this a terrible night for demonstrations, but I need to get this done. So I'm going to turn it on and try to do some experiments. So first of all, there is a very small electric spark that I can show you with my knuckles. And, you know, the first question students ask is, does that hurt? And the short answer is, yes, that hurts. And that was one of the methods that Franklin used to establish the conclusion that he reached. So here's what he was wondering. Could it possibly be that the huge lightning bolt that comes out of the sky be the very same thing as the little teeny tiny crackly sparks that he got when he pet his cat? Or the little spark that you could get using a Leyden jar, which today we call a capacitor. So he carried out a series of experiments, and I'm going to try to illustrate them with this machine, and just wish me luck. So first, when the machine is on, you can see that it builds up charge, and that when I touch it with my knuckles or something, or my tongue, no, I'm not going to do that, that you can see a little static discharge. On a really dry day in my classroom, we've gotten lightning bolts to go about a foot or so, 10 inches at least, or 30 centimeters. So it can be impressive. Right now it's just not that impressive. And so what can I show you? I can try to show you that when I take some confetti and I put it inside a metal container, what do you predict will happen if this confetti is just like the palm fronds? Right? So I turn the machine on. You see the pom-poms going up. It's getting a little bit better now. I'm going to remove that maybe and put this metal cup on there. What do you think will happen when I do this? You were hoping for something more exciting, I'm sure. But even in this lighting, with that noise, you can basically see nothing is happening, except, yes, it's still sparking when I touch it. Okay, now the sparks are a little bit larger. They don't have the fronds, the pom-poms to compete with. I'm going to take these same pieces of paper and dump them into a paper cup and stick it on here and see if anything happens. And the short answer is nothing happens because the electric forces just are not strong enough. If you talk with veteran students who've seen this demonstration in my classroom, they can tell you all about how they were mystified because when the confetti was put into a metal container, nothing happened. When it was put into a styrofoam cup, which I don't have, I have a paper cup, the confetti would come flying out of this. Each would pick up an electric charge and repel against each other and come out. I guess the only thing I can do that's exciting this evening is just electrocute myself in the name of science. One thing I wanted to suggest is that Franklin carried out a series of experiments, and I'm going to put the pom-pom back on to kind of show it, that when you bring a metal object near a charged object, what do you think will happen? Well, let's see. The short answer is not a lot is happening. The sphere is still electrified. When I touch it, I'm grounding it and it discharges. When the wind blows, it looks like a lot is happening. But this metal scepter, like as if I were royalty, is not really doing anything. I also have a wooden stick that I put in the pencil sharpener, created a sharp point on it, and I bring it near, and it seems to be playing with the tip a little bit, but nothing very dramatic. When I do the flat end, again, about the same response. Nothing very dramatic at all. When I bring this PVC pipe near, nothing interesting happens. Okay, nothing significant. When I bring a nail near, now you see a dramatic effect. And this is a file on a plastic handle, so I'm going to try to bring it near. And you see this is behaving almost like a Harry Potter wand. When I bring it near, you can even maybe see a little bit of electric spark, very small, not like my hand, but it dissipates the charge. So Franklin discovered that it matters what material you work with. Wood doesn't do anything, metal does, but here's a nail. The sharp point of the nail has a major effect. The head, flat part of the nail, has much less effect until I touch it. But if I bring it near, not much happens. I bring the pointy end near, it's much more dramatic. So Franklin figured out that having metal with a sharp point on it can dissipate the electric field and make the sparks very small compared to otherwise. So he took all this information and took a piece of metal, sharpened it, and put it on the roof of his house. I'll shut this off, for the dramatic effect. So he put a piece of sharp metal on the roof of his house, and guess what? It did not get struck by lightning. He put this on top of what became the University of Pennsylvania, and he put this on top of the building that became Independence Hall, where the Declaration was signed. None of those buildings were affected by lightning strikes that particular summer. So he went and published this in Poor Richard's Almanac, the January 1753 issue, and right away colonists up and down the eastern colonial seaboard went to their local equivalent of Home Depot and Lowe's and bought some sharp iron and stuck it on the roofs of their buildings, and it had a dramatic effect. The buildings that had this on top of it were not struck by lightning. So two things happen. The point of the metal dissipates the electric field, and if there is a lightning strike, the metal would conduct the lightning bolt through the metal into the ground, not going to the wood of the house in the process. So this was the first time that electricity was found to be a discovery made by the process of science. I've kind of skipped a couple things. Maybe I should go back and mention that there's a famous image of Franklin flying a kite in a storm with an iron key hanging from the kite string. Please don't do this. The next 4 people who tried to duplicate that experiment were all killed. So Franklin was a busy guy, revolution to plan. He set up a kite flying out of his office window at his home in Monticello, I think, Virginia. And he set up a configuration like this. So there's 2 bells here with a ball, metal ball on a thread. And the kite would be set up at the beginning of the day, and one bell would be connected to ground and the other one would not be. And so what would happen is, if a storm were brewing, then the kite string would become electrified like the cat's hair, and the bell closest to the kite string would attract to it. Oh, so here's what just happened. My camera stopped recording, and I actually had gone on and talked for a while longer, but none of it was recorded. So what I've done is I've moved the setup indoors, and here it is the next morning, and I just want to finish what I was trying to explain to you. There's more to this to go. So where I left off was trying to explain about this. So Ben Franklin had a device like this set up. In the morning, he would start flying a kite and then tie off the kite string outside his office window with one of the kite strings attached to a bell. The other bell was grounded, connected to Mother Earth. In between the 2 of them is this metal clapper hanging on an insulated thread. So what would happen is, if a storm were brewing, it would electrify one of the bells. The neutral clapper would be attracted to it, because neutral objects are attracted to charged objects. When it touched it, it would ring the bell. But at the same time, these are two metal conductors. So the clapper would become charged with the same sign charge as this bell. Like charges repel. So the clapper would swing away and touch the grounded bell. But when it touches the grounded bell, it loses its electric charge and becomes neutral again. So the effect is, and I'm just doing this by shaking my hand, right? The effect is the clapper bounces back and forth between the two bells. And if I shut up for a moment and you listen, what you're hearing is the sound of the world's first electric doorbell, invented by Benjamin Franklin in the summer of 1750. So this is what alerted him to when a storm was approaching. The painting is inaccurate. It shows him wearing his three-colored hat, standing out in the rain with an iron key hanging from the kite string as a dark storm is hitting. The inaccuracy is he wasn't standing out in the rain. He was too intelligent and realized that maybe a lightning bolt would come down that kite string and kill him, like the next 4 people or so. So what he had done is he tied the kite string off to a fence post, and then he himself stood where it was dry underneath a shed nearby, watching the goings-on. Now the purpose of all this, of his experiment, was to validate that all the experiments he had done by petting his cats and experimenting with the Leyden jar was exactly the same physical phenomena as the lightning that he could pull out of the sky using the kite string. So the purpose of the iron key was to build up an electric charge drawn from the sky to compare it with what he had done in the lab. So I'm going to turn this thing on for a moment, find the on switch, there it is. And what he did is, after the storm went by, not daring, he went up to the iron key and with his knuckles said, oh yeah, hey, that's about the same result that I got when I was playing with the Leyden jar. And, I guess I need to move so that you have a background, we can see this better. My shirt helps, right? Okay, so, yes, this hurts. And that's what Franklin was doing too. He said, oh yeah, that's about a 3. Oh, that one's a 4. Yeah, the same thing. He also collected electricity from that iron key and put it on the Leyden jar and verified that it had exactly the same results. So I know, you like watching me electrocute myself. Okay. It's kind of distracting you. Okay. So, author's message. Franklin applied the scientific method. And from all of that, starting with just being curious about what happens when he pets his cat, from all that, invented the lightning rod, realizing that pointed metal dissipates an electric field. Rounded ends don't, non-metals don't. That if a lightning bolt does hit a lightning rod, using metal wires to conduct it to ground will divert the electric lightning bolt strike along the metal path. This was the first time that science was seen as being practical for the common man. And I began this lecture quoting from Isaac Asimov's article. Everything I presented is really drawn from that article. And so I thought I would toss in a quote from the end of his article because he expresses it well. He wrote, "It was clearly a product of science. For the first time in the history of mankind, one of the scourges of the universe had been beaten, not by magic and spells and prayer, not by an attempt to subvert the laws of nature, but by science, by an understanding of the laws of nature, and by intelligent cooperation with them." Excellent line. So let me expand on that. Before these experiments, science was natural philosophy, something not for the common everyday man. Following the invention of the lightning rod, the society understood the value of science and technology improving the quality of life. And that's what led to science being part of the required curriculum. That's what led to the building of the science building on our campus and putting it into the requirements for graduation and electives in college. With the current crisis with COVID-19, we're again turning to science to help us learn how to manage this and come out of this ever better. Now, he mentioned in his conclusion here, not relying on magic and spells and prayer. So I just want to speak to that for a moment and point out that I have a number of students who mistakenly think that either you're religious or you're scientific. You can't be both. That is totally incorrect. Many scientists were deeply religious, and you should recognize that religion is really trying to help you make sense of why you are here and to get you to contemplate the distinction between good and evil. Science is dealing with how the universe works, and it's like a beautifully complex puzzle, ever greater level of complexity to it. Science is kind of messy at times, hence our initial modeling for how COVID is going to affect the population has become refined as we collect more data and we hypothesize and say, oh, okay, so the transmission is primarily this way and not that way, and the population is doing this, and our models are ever improving. And we're looking to science to get us to manage stuff like this challenge and come out of it. In my physics course, like all the other science courses, there are ever greater levels of complexity. And it's like a video game when, oh, I've mastered level 3. Well, great, now go to level 4. So in chemistry, we've had some very basic chemistry, and now you can go to organic chemistry, and you go to quantum chemistry, I kid you not. In cosmochemistry, in physics, I've been teaching you classic physics. Now you could go to quantum physics and learn about Schrodinger's equation and quantum tunneling. Really good stuff. And then if you want to go another layer, you can go study what the heck is dark matter and dark energy. And then above that, who knows? But there are these deeper and deeper levels, or higher and higher levels of complexity and challenge. You can make a career out of it. And what I want you to consider is applying your talents, applying your curiosity. This started by petting a cat. And the scientific method, and being open to exploring your understanding of things. There are people today who have closed off their minds to science as being helpful. So science and technology together is what's letting you get a newer version phone and laptop and everything else that you enjoy in your quality of life. I want you, we, the science department, want you to get involved. Apply your curiosity, apply your talents, apply your intellect. There are problems that need solving, and advancements in science aren't made by old codgers who've been doing the same thing for decades. The revolutions in our understanding in science come from two sources. Newcomers to the field, so someone who was, let's say an accountant, and now they decided, I'm going to study paleontology, and they make discoveries, they make an advancement in our modeling and understanding of things because they're new to the field and they look at it from an outsider's perspective. The second group are young people who don't really swallow everything that their instructors tell them. They say, well, okay, my instructor said that, but is that really true? And that is how science advances. A little bit of skepticism, a lot of research with the scientific method, not being prejudiced against what the data is showing you. And about every generation or so, our understanding of the entire universe advances thanks to people like you. So, I do want to toss in one more thought while the camera's running. In the current COVID-19 discussions out there in our nation. There is one group that feels like, oh, you scientists, you're only focused on human health, you've ignored our economy, we can't just shelter in place and let and die because we're unemployed. So I need to point out to you that scientists generally look at the big picture, and we understand that the economy is like a living organism. It can be healthy, it can be sick, it can grow and prosper, it can become ill and contract, and it can even die. So we look at that as well. 100 years ago, the Spanish flu broke out, spread around the world. Within the United States, various cities, basically on their own, decided how they were going to manage the pandemic. And some cities went into a very strict lockdown, and some cities said, no, we need to, the economy is more important. Well, 100 years later, we can look back at the records historically and see, well, which one worked out better. So one group is sort of like, you work so that you can live, and the other group is like, you live so that you can work for us. And of the two, the cities that valued human life became the cities that had the healthier economic growth afterwards. And the cities that valued, making money for the top end people and treating the population like, oh, you're our slave labor, come work, I don't care if you get sick. Those are the cities that people were not attracted to. So why would I want to go work for someone else my whole life when I could live the American dream and make advancements? So those cities that were trying to save the economy long term didn't work out as prosperous as the cities that valued human life and respected that. So keep that in mind as you work through solving the challenges facing you today, because after this one, there's going to be another challenge. And throughout your life, these challenges are going to be coming along. Ciao.